Come back to another video. So I'm just doing a revision video on chemical equilibrium with you guys. So let's look at this topic. So we'll first deal with types of systems and La Chatelier principle, concentration, pressure, and temperature, endothermic and exothermic reactions. And yeah, so let's get into that. We have types of systems, right? So there are two types of systems in chemical equilibrium. We have the open system, which continuously interact with its environment. It constantly interacts with its environment. So for example, when you are boiling a pot using a container with a lid, water vapor will escape from the container to the surrounding environment. So open system exchanges energy and matter, right? So take note that in the above system, water vapor is escaping from the container because it is open. So it means condensation cannot take place, which is the reverse reaction. So here in the open system, it means a forward reaction happens. So there's a forward reaction. When that pot that is boiling is interacting with the environment, a product will be formed. So we have an open system, which is an exothermic reaction, right? Exothermic reaction, forward reaction, open system. I hope I'm just summarizing that. So whenever you see an exchange of energy and matter, that exothermic reaction, but you first have to look at the change in hydrogen if it's less than 0, right? So this is in an open system, we have a forward reaction. And then here we have a closed system. So in a closed system is whereby we're boiling water in a pot, but the lid has been closed and isolated from its surroundings. So in a closed system, we have exchange of energy, but not matter. So whatever the contents of what is in the pot is not interacting with the outside world. So in this system, is the reverse reaction will take place in the system, right? So when you open the pot, right, the system is interacting with other things that are matters that are on the A. So it is interacting with that matter to form a product. But when you have closed the pot, the system is not interacting with any matter to form a product. So it means it's a decomposition from a product back to a reaction. We react two things, maybe it's 2SO plus 2 O's, and they will give us 2SO, right? 2SO3. So that's what you have to know. Let's take H2O there on the top. We have H2O. H2O is a reaction, right? That point that is pointing towards the H2OG on your right hand side is what we call a product. So H2O, it's in a, so in this instance, reverse reaction will take place in this system whereby the pot is closed, right? The system is not exchanging or isolate. The system is isolated from its surroundings, so it's not exchanging matter with its surroundings. So that is a closed system, which means reverse reaction is happening when a system is isolated from its surroundings. But when a system is open and not surrounded, system is open and surrounded by its surroundings, not isolated by its surroundings, there we will have a forward reaction. So remember, let's summarize this. Open system, it's a forward reaction. So the what is inside, the contents of what is in the pot is interacting with its environment. But when we have the closed system, it is a reverse reaction. So another thing, a reaction is reversible when products can be converted back to reactant and vice versa. And there's a hint there, do not omit underlined keywords when you're trying to explain what is a reaction. So a reversible reaction consists of a forward reaction and a reverse reaction, right? So when you have those two arrows, look at that blue box. A forward reaction is going to the right direction and a reverse direction is going towards the left direction. So in a chemical reaction, when you have a forward and a backward reaction, a forward and a reverse reaction, that means the whole thing is reversible. That is a reversible reaction. It consists of a forward reaction and a reverse reaction. So reverse reaction reach equilibrium in closed system. Note, reversible reaction reaches equilibrium in a closed system, what we have just explained. So initially, the rate of the forward reaction decreases since the reactants are being used. So one thing you should know that let's look at that blue box. We have H2O in liters. What you have to know is that when you increase H2O, when you're trying to increase H2O on the left hand side, it will not increase, right? Instead, what will increase is the forward reaction. What will come out of it is what will increase. So just know, if you're trying to increase the reaction, the system will act against it. That is La Chatelier principle. The system will work against that increase that you are trying to do. So you're increasing the reaction, it will not allow you, but it will increase the product. And then that's where we get the forward reaction. But when you increase the product, which is the H2OG, it will not, the system will work against it because it is in equilibrium. You are disturbing whatever that is happening when you're trying to add more H2OG into the system. So when you are increasing the H2OG, the system will work against it. So when you are trying to increase, but the system will decrease it. So when it's decreasing it, it will have a reverse reaction. So in the H2OI, that's where we have the reaction. And then in the right hand side, the H2OG, that is where we have the product. So you increase the product when the system is in equilibrium. The system will work against that increase you are trying to do, right? When it will work against that increase you are trying to do, and it will increase the other side. So you are increasing the product, you are actually decreasing it, and you are increasing the opposite, the left hand side. So when you're increasing the right hand side, you are actually decreasing it, and you're increasing the left hand side. But if you say you decrease H2OI, if you decrease it, the system will work against you and it will increase it. So you see, it's the opposite. And if you decrease the H2OG, the system will work against you. It tries to do what you are not doing. That is the La Chatelier principle. So you are trying to decrease, the system will increase. So we can look also at chemical equilibrium. Is a dynamic equilibrium when the rate of the forward reaction equals to the rate of the reverse reaction. That's it's in equilibrium. Let's say you have a bottle of Coca-Cola. There is acid and water in there, right? They are mixed, but you cannot see the difference because they're in equilibrium. When they're in equilibrium, they are the same. The forward reaction is equals to the rate of the reverse reaction. So you have the same thing that is combined, and it's not, nothing is isolated there. So everything is combined. It's not acid here and water there. No, everything is combined. Let's say, for instance, but when you see that bottle, you don't see the acid is there, the liquid is there. No, it's one thing. So that is equilibrium. Now you can look at these two figures. Like in figure 1, the dotted line is the forward reaction and the red one is the reverse reaction. So the forward reaction starts high. You can see on those y-axis it starts high and then starts to decrease the speed until it travels at a constant rate. But the reverse reaction starts low at 0. You see, it starts low going and ends up high before it enters into a constant rate. In that constant rate, they are at equilibrium. So this graph is for the reactant also starts high and end up low, but the product starts low and ends high. You can see that is there and then ends in equilibrium. That is for graph 2. So here are the notes in both figures 1 and 2. The reaction has reached a system of dynamic chemical equilibrium. So a chemical reaction has reached chemical equilibrium at T1, where the curve flattens out to become horizontal. After T1, the rate of the forward reaction is equal to the rate of reverse reaction. After T1, concentration of product and reactant remains constant. So that is the explanation of those two graphs. Which one starts high, which one starts low. And avoid saying things like forward reaction is equals to the reverse reaction. No, it's the rate of forward reaction is equal to the rate of reverse reaction. Not forward reaction is equals to reverse reaction. And concentration of the forward reaction is equals to the concentration of the reverse reaction. Stop saying all those things that are highlighted in red. Then we have factors that influence the position of a chemical equilibrium. This is a chemical equilibrium. We have it here, but there are factors that actually affect that. And that's where the Le Chatelier that I've talked about previously is going to come in. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. That's why I said when you're trying to increase a reactant, the system will decrease it and increase the product. When you're trying to increase the product, the system will reject what you're trying to do and decrease the product and increase something else, which is the reactant. So it will always work against you when it's in equilibrium. Please take note of that. And then you should know the following definitions from grade 11. Exothermic reactions are reactions that release energy. That is a forward reaction. And then endothermic reactions are reactions that absorb energy, which are the reverse reactions. So remember, exothermic H is less than 0, endothermic H is greater than 0. So when applying the Le Chatelier principle by changing equilibrium conditions, the equilibrium position will shift in such a way as to counteract, oppose the disturbance. So this reaction is in equilibrium and we are trying to increase the temperature or decrease the temperature, right? So when you're trying to increase the temperature of a reaction that is in equilibrium, the endothermic reaction will be favored. So remember that when you increase temperature, endothermic reactions are favored. So meaning the reverse. A reverse will happen there. So when you are trying So a reaction that decreases the temperature of the system will happen. You are trying to increase the temperature, right? But the reaction that will decrease the temperature that you're trying to increase will happen. So what you are trying to do will not happen. So that is endothermic reaction. And then when you decrease the temperature, exothermic reaction increases. So that is when you are trying to decrease the temperature. So the system will work against you and do the opposite of what you are trying to achieve, right? So the exothermic is like burning of a candle, roasting iron, burning sugar. That is exothermic reaction. So a reactant that increases the temperature to the system will happen when you are trying to decrease the temperature. Just know that you decrease the temperature, the reactions that increase the temperature will happen. But when you increase the temperature, the reaction that decreases the temperature of the system will happen. So you increase, the system will decreases. You decrease, the system increases. Just like that. And then we have concentration. So concentration only focuses on aqueous and gases. So when you increase the concentration of a reactant or a product, increasing the concentration of a reactant or a product favors the reaction that uses the substance. So adding a reactant, increasing a reactant, that's what I've said, favors the forward reaction, right? Or adding or increasing the product favors the reverse reaction. And then decreasing the concentration of reactant product. So when you decrease the concentration, you favor the reaction that increases the concentration. You are decreasing it, but the favors that increases the concentration of a substance will go up, will fight. What are you trying to do? We are settled and you are here trying to fight us. We are going to repel whatever you want to do to the system. So removing a reactant, reverse reaction will be favored, right? When you are removing, we have 20 reactant, but you are moving it to 15 reactants. What is in the left hand side? So reverse reaction will be favored, which means when you are removing, so the forward reaction is also favored if the concentration of a product is decreased so that more product is formed, right? When you decrease the product, decrease a product of a system, more products are formed. Remember, when you're trying to decrease something, the system will increase it. So removing a product, forward reaction will be favored. Yes, you should know that when you decrease a reactant, the system will increase it. And when you decrease a product, the system will increase it. So the reverse reaction works for the product, and the forward reaction, the reversal, what is this? The reverse reaction produces the reaction, but the forward reaction produces the product. Know that. And then we are at pressure. Pressure focuses on gases. So increasing or decreasing volume. It favors when you increase pressure. It favors the reaction that forms the smaller amount of gases side with gas-less molecule. So it will favor when you increase gas, it will favor the side that has less gas, and when you decrease the pressure, it favors the reaction that forms more amount of gases, so the side that has more gases between the left and the right hand side. So pressure of gases will not affect the position of equilibrium if there are equal number of moles of gases, reactions, and product. So if the number of moles are the same on the left hand side and the right hand side, the equilibrium will not be affected. Moles are the coefficients. You can try to look at stoichiometry calculations then you will know exactly what moles are for grade 10. I have a video that on my channel. You can check that one out. You also have to know how to balance a chemical equation, so check that out in my channel for grade 10. I have posted it. So here is an activity that you can do and answer the questions. I will show the questions. You can just pause this video, do this activity, and I will show you the answers. And here are the answers. To the questions. You also have hints of how to answer this question here. This is a guideline for grade 12. And you also have example 2. You can pause the video and do this activity. And here are the solutions. And then you can see this note of change in pressure. Step to be followed in case of change in pressure, and balance the chemical equation. So yeah, you see the moles here. In front of A we have 2. That 2 is a mole. And then in B in front of B we have 1. So those are 3 moles. And then in the right hand side we have C. C has 1 plus D also has 1. So it's 3 and 2 moles. You see, so the sides are not the same. So remember what we talked about with regards to pressure. Pressure of gases will not affect the position of equilibrium if there are equal number of mole gases, reactant, and product. So you see, a forward reaction has 2 moles. A forward reaction has 2 moles and a reverse reaction has 3 moles. So when you combine A plus B, they give you C plus D. So A plus B is a reaction and C plus D is a product. So the product is the forward reaction. When you combine A and B, we get a forward reaction which will give us C and D. C and D is a forward reaction. A and B is a reverse reaction. Keep that in mind. And then determine if the forward or reverse reaction is favoring using the Le Chatelier principle when pressure is increased or decreased. State how the concentration of the reactants of the product change. So this is example 3. You can pause the video, do it, and then come and see the answer. Here is the solution to example 3. Now we have example 4. Pause the video, do the example 4, and this is the solution to example 4. So look at that. We are given H2 plus S, the reverse reaction. We have H2S, and you are given a hint that change in H is less than O. So that is an open system. So remember, this is an open system. So that is how you have to check whether it's an open system or a closed system. There you are given an open system, and number 1, you are also given a open system. Let's check. Yeah, still an open system. Yes, that's how you are going to answer. Look at whether it's a closed. Yes, number 1 here, we are given a closed system. So that is how your answers will be affected, because here it say 1.2 is forward reaction endothermic or exothermic. You see, and you are given H is greater than 0, and here the answer says it's endothermic. So those are the things that you have to check. And also in example 4 here, the following reaction reaches chemical equilibrium in a sealed container at 70 degrees. Sealed container, that is a closed system. Na N2O This is the reactant is that, and then we have the product. What is the effect of adding more H2O? We are adding more, so we are increasing the reactant, which means the reactant will decrease and the product will increase. Look at the answer. Increasing the concentration of N2O4 will favor the reaction that decreases the concentration of N2O4. So forward reaction is favored. The concentration of HO2 increases, or more number of moles will be formed. So you see, it's the opposite. You're trying to increase something, the system will decrease it and favor the opposite sides. Thank you very much for watching, guys. I hope you enjoyed this video. I will do equilibrium constant on the next.